Geometry, section 10.4, perimeters and areas of similar figures. Take a look at the drawing that I have here with the three rectangles. I'm going to refer to these as small, medium, and large as I try to make comparisons among them. First of all, I'd like you to notice that we can make a comparison of the sides. And 4 to 8, if I put that into a fraction, would be 1/2. And just the same, if I do with the other sides, 3 to 6 is also a fraction that reduces to 1/2. So the similarity ratio, that's going to be a word that's in our theorem here in a minute. Similarity ratio, sometimes the book calls it ratio of similarity, that's the same thing, would be 1/2 as it relates to the small and the medium rectangles. The similarity ratio is 1/2. Okay. Now, what if we did the same thing for small to large? 3 to 9. 3 to 9 is 1/3. 4 to 12, 4 over 12 is also 1/3. Notice that these are the same number. The reason these are the same number is because these rectangles are similar. Of course, all kinds of rectangles could be not similar. That would mean that they are different shapes. But if they are the same shape, different size, that's what we called similar way back in several chapters ago. And that's what's happening here. And if I even compared the second and the third rectangle, I won't write these down, I'll just say it. 6/9 is 2/3. 8/12 is also 2/3. So if I said, what's the similarity ratio from the medium rectangle to the large rectangle, it's 2/3. By the way, sometimes the book will use colon notation. I'm fine with colon notation too. I like fraction better. The point is that it needs to be reduced. You should not give me 6 to 9. It should be reduced to 2 to 3, like that. And I think probably you should tend towards fractions anyway. It works better mathematically. Okay, now here's the point to the section. Notice the perimeter of the small rectangle would be 14, right? 3 plus 4 plus 3 plus 4 would be 14. 14 over, notice the perimeter of this one would be 28. And that is 1/2. That's the same number that we got when we compared the sides. Okay, and I won't go through the rest of it. You could check it if you want to, but if you did the perimeter of the large one and then compared the perimeter from small to large, you'll get the same number that we got when we were comparing sides. And that's going to lead to the first part of the theorem. This theorem says perimeters and areas of similar figures. If the similarity ratio of two similar figures is A over B, or A to B with a colon notation, A colon B, I like the fraction though, then two things happen. The first thing we just kind of proved there is the ratio of the perimeters is also A over B. If this is A over B, then this is going to be that same A over B. If it's 1/3, then the perimeters also are going to be 1/3. Okay, now getting a little bit more complicated, let's think of the areas. Let's calculate 3 areas of rectangles. Let's multiply here. 3 times 4 would be 12. The area of the small rectangle is 12. 6 times 8 is 48. And 9 times 12 is 108. Check that on your calculator if you want to. It's 108. Okay? Now, if I compare the area, remember that the comparison of the sides and the comparison of the perimeters from small to medium was 1/2. If I compare the areas, 12 over 48, that's not 1/2, that's 1/4. Now think about that. 1/2 and 1/4, are they related? One-fourth is actually 1/2 squared, right? I could propose to you, and I'm about to prove to you, and give it to you in a theorem, that the ratio of their areas is the ratio of the sides squared. Okay, and I'm just going to prove that anecdotally a little bit further. Let's compare small to large. 12 over 108. We got 1/3. Reduce 12 over 108, you're going to get 1/9. Why? Well, because on this one, 1/2 squared, or maybe more like the way this is going to show here would be 1 squared over 2 squared, either way, is 1/4. Here, we got 1/3. 1/3 squared, or 1 squared over 3 squared, same thing, is 1/9. And even 48 over 108, where we got a similarity ratio of 2/3, 48 over 108 is going to be 4/9. Why? Because 2/3 squared is 4/9. Okay, so that then anecdotally proves the second part of our theorem, which says the ratio of their areas is a squared over b squared. Still this, if the similarity ratio of two similar figures is a over b, then the ratio of their areas is a squared over b squared. Okay, so a few examples. This says the triangles below are similar. Find the ratio, larger to smaller, of their perimeters and of their areas. Okay, so let's just quickly get their perimeters. The perimeter here, 4, 5, 6 would be 15. The perimeter here would be, little mental math, 13.75, 18.75. Okay. And 15 divided by 18.75, you might be able to figure out how to use the fraction, but I'm using a graphing calculator, but you could probably work in your fraction button on the scientific calculators. It's an easy decimal anyway, 0.8. It's 4/5. Now the similarity ratio would be 4/5. Excuse me, the ratio of their perimeters would be 4/5. Now look at the triangles and see if we would have known that before actually calculating it on perimeters. This is the point. I didn't really need to do that with perimeters. I wanted to show you. Couldn't you line up the two smallest sides and compare that way? 4/5. Oh, I beg your pardon. It did say larger to smaller. I believe I should be doing 5/4, not 4/5. 5/4. Larger to smaller. 5/4. And if you want to compare the longest sides, incidentally, this is not a right triangle. We learned earlier in the year that a 3, 4, 5 is a right triangle. This is a 4, 5, 6, which would make it not a right triangle. Test it out if you like. We could compare the longest side, 7.5 over 6, and reduce that fraction. You're going to get 5/4. Same thing with 6.25 over 5. So that would be 5/4. And then quickly now, you don't have the ability to calculate the areas of either one of these triangles again because that's not a right triangle. You couldn't plug in to 1/2 base times height here because that other side is not a height. But it doesn't matter because of our theorem. Our theorem would give me the ratio of their areas, which would be 5/4 squared, which is 25/16. Okay, now I kind of made a mess of that slide there, so let me just erase it and show you theirs. 5/4 for the similarity ratio means 5/4 for the perimeters means 25/16, which is 5 squared over 4 squared for their areas. Next, it says the ratio of the lengths of corresponding sides of two regular octagons is 8/3. The area of the larger octagon is 320 feet squared. Find the area of the smaller octagon. I like to think about it in some terms. I like to think about it like being in levels. Level 1 is length. Okay, that's where similarity ratio and the ratio of perimeters lives. Level 2 is area. That's what we're being told here about the larger octagon. Okay, now the fact that it's an octagon means nothing. You might get scared away by the fact that it's an octagon, and we had a pretty complicated formula for that. That's not what they're asking us to do here, though. We're just comparing numbers. So here's what you would need to do. This fraction is a similarity ratio. That fraction lives on level 1. To take it to level 2, we'd have to square it. Take 8/3 and square it, and you'll have 64/9. Now you can set up a proportion, 64/9, and it's equal to a fraction. Now think about this. Where would the 320 go, top or bottom? If you answer top, you would be correct. The reason that it would be in the top is because it's the larger octagon. Okay, and then we'll want to solve for the one on the bottom. And we did cross multiplying a lot, and I'm trying to keep this video shorter, so I'll just roll to the answer here. Cross multiply and solve there, you'll get 45. X is 45. 45 what? Feet squared. It's the area of the smaller octagon. Okay, moving along. This one's very similar. Something like a field is and I'll leave it there a second if somebody wanted to go through this example. But something like a field that you have to put seed on, since it's two-dimensional, is going to be like area. Okay, so I'm just going to move on to the last one. The areas of two similar pentagons are 32 inches squared and 72 inches squared. What is their similarity ratio? And then what is the ratio of their perimeters? Okay, so this is a problem where they're giving us information that's on level 2, and we need to take it back to level 1. So here's what you do. You'd go 32 over 72. And just as going from level 1 to level 2, you have to square it. Here we're on level 2 and we're going back to level 1. We're going to have to square root. Okay, now look at those numbers and see if those are going to be easy to square root. 32 over 72. That's because we should reduce the fraction first. You don't want to square root 32. You don't want to square root 72. You're going to get wild decimals. It would still work out if you have the right calculating tools, but it'd be easier if we would just reduce this fraction. Okay, so for example, they're both divisible by 2. That would be 16 over 36. Actually, you can go farther than that. That would actually be 4/9, because they're both divisible by 8. Okay, now understand, and this is the key point to this lesson, 4/9 is not the similarity ratio. 4/9 is still on level 2. All you did was reduce a fraction. To take it from level 2 to level 1, you have to square root that fraction. That would be 2/3. 2/3 is the similarity ratio. 2/3 then would also be the ratio of their perimeters. Okay, thanks for watching.